Yeah, thank you.
Right. If I press here, yes. Now it should be better. And I just a short introduction of myself. Ole Saastad, come from University of Oslo, background in chemistry. I've been using supercomputers for quite some time. Yeah, I've been involved in several of the architectural things and so on, but all in all, I've been very obsessed by using the computers effectively so that you are using it 100%. It came from the time when computers were scarce and they were expensive, and it was hard to get by. Then I started trying to run, either we got hold of our own computers or we start using microprocessors. And that brings us over to the clusters, because in the old days you had one CPU and one big computer. Suddenly you could start running scientific applications on your office computer, but it took 100 times longer than the supercomputer. But who cares if it took a week when you have to stand in line 3 weeks in a queue? Which brings up the queuing system. In order to have 100% utilization of a cluster like we have here, the queue needs to be infinitely long. So there is a trade-off here. If the queue time is short, the utilization goes down. And if you have wide areas on the utilization map, that's wasted money. Since the machine like Betsy cost over 100 million Norwegian, any wide areas on the map represent a big cost. So some of us like to have an infinitely long queue, but the users want a very short queue. So this is not easy. And in order to have the poor queuing system trying to deal with this is even worse, because to set up such a queue is like having tiles of different sizes on a floor. It's not easy to fill the whole floor space when the tiles you not have an infinite amount of tiles of different sizes to put in there. So the queuing system do a very hard job trying to schedule. Of course, which there is no closed equation to do so. It's more like a traveling salesman problem or knapsack or whatever kind of these problems you want to address. So queuing system try to do as best as it can. Anyway, we have to try to use the resources in the best possible way, not only because it's shorter runtime for us, but also if we have shorter runtime, get more jobs done and other users can use the system. So I put up here that computers normally run programs, which not everybody really understand why they run programs. So you need to compile and write your program in the best possible way. We will talk about some resources, to ask for resources and whatever. Then the environment, that you can set up an environment for your job. But most important, but not the least, the most important one is scaling. As you can see, this guy who's bought the 2 turtles and he complaining doesn't go any faster. So this is important. Scaling is one of the most important things when it comes to modern computers today. It was easier 40 years ago. We had only one CPU. Then it was easy. You have to do some vectorization and so on, but not any question of scaling was pointless because there was only one CPU. Okay, running programs, interactive runs. For those who are doing development, are doing production development, have short runtimes where you sit at the keyboard and screen and run and so on, interactive resources are very, very important. The local cluster in Oslo has a significant fraction, not a big fraction, but a significant fraction, less than 0, of interactive nodes where you are allowed to run jobs. And newer computers on the national systems like the A2 that Einar showed will have an interactive partition where you are allowed to actually run jobs. This is free for all. It's a buffet, as Bjørn Helge talked about. So you will have to fight with the others. And there is a potential that you can screw up for everybody else. But this is a cost you have to live with if you want to run interactively and sharing. So interactive jobs are for a lot, for some people, very, very important. So hence we are addressing that since we have it's easier to do it here locally because it's a very small system. It's not so easy on the larger national system, but the newer one like A2 will have an interactive partition. Then you, of course, you can reserve a node with for interactive use if you reserve the whole node for some time, for a few hours during the office hours and run there. And then set up for batch execution, which is the normal way of doing with a supercomputer. This has been done for over 50 years or 60 years. People have run in batch, and in the old days, you have a deck of cards in a box that you went to some hole in the wall where some nice person took your box of cards or deck and processed them. And the next day you could find your listing. If you're lucky, next day or the next week, you could find your listing on a shelf with your name on and the output of the program. So batch computing is nothing new. We'll talk about some resources and so on. Yeah. Interactive usage of the front end. Some people run interactive jobs on the front end. That's okay if they are short, if they don't take all the resources, I mean the memory. So copying files, of course, is only possible in many cases on the front end. Compiling and testing, so fine. Anything that takes longer than if you can wait, sitting there waiting and tolerate the wait, I think it's okay. If you cannot tolerate the wait and sit tied to your screen and keyboard, then you shouldn't really run on the front end. So few minutes, 10 minutes, jobs are fine. But anything longer or anything that uses a large fraction of the resources like memory are no good on the front ends. So there is the documentation that you can read on the screen. So yeah. Bjørn Helge talked about the batch queue system. I'll deal with some more details of how to use it and so on, and so how to get the most out of it. What Bjørn Helge didn't mention, he mentioned only that you have to use a bash script. That's the most common. 99 point something are using it bash or shell script. Born again shell is for base bash is called, yeah. So it's a modern version of the old SH shell. But you can use Python, Julia, R, any kind of scripting interactive language that uses the hash character as a comment you can use. So I have examples with all of those. Like in Python, Bash, or Julia. So you see they are all the same regarding the comment sign instead of on the top. There's a different way of dealing with things. The first is bin bash, which is not the most portable way, the user bin environment, and then bash could you be used instead of Python or Julia. And the last line is just echo hello world, and then it's the same on, it's a different on the different languages. R is also good. Lua is not, because it doesn't use hash as a comment. So Lua, while Lua is a nice language for sysadmin work, it's not really usable for this because it uses different comment sign. Any language that are interpreted can be used for this if it has a hash as a comment sign. There are some big projects like the ESM project, NOR ESM project uses it's extensively use of Python as the scripting language for submitting jobs. Read the documentation. I cannot state this more often. So how to launch your executable? If you have, I say, launching your MPI executable, and I become lazy in my later days, so I just use a.out as an example, and also when I'm by myself. Serial, a.out, OpenMP, which it's parallelizing with threads. MPI, you have to use MPI run or srun. There are different ways of launching MPI jobs. You have also MPI exec. They more or less do the same thing on our systems. MPI run, MPI exec, etc. are the MPI versions that we have that we support, which is the Intel one and the OpenMPI one, they are integrated into Slurm. So if you use MPI run, Slurm will pick that up and use the daemon running on each of the compute nodes to launch your job. But if you are in the situation where, unlucky situation where Slurm is not set up to do this, it will use SSH to log into each of the compute node and then launch your program, which might take somewhat longer. But generally, MPI run or SRun are generally the same on our system. You can use both of them, which one you prefer. But MPI run has a lot of options that SRun doesn't have. So you have to, if you want to use some special option into MPI run, you have to use MPI run. And of course, if you use Intel MPI run or OpenMP MPI run, the syntax of any option differ widely. So you have to really know what you're doing. But if you just say MPI run, it's fine. You don't need to specify any kind of number of CPUs or whatever, because that's already done in Slurm, and Slurm will pick that up, put that into the MPI run or put that into the MPI, and your job will run at the number of ranks that you specified in the Slurm file. So running the programs, and as I said, the most use of computers is to run computer programs. The small fraction that don't are on museums. You have to request resources, and Bjørn Helge touched upon that, what to ask for and what to request and so on, and then how to use Slurm. And storage, scratch, and persistent. There is a big difference on those. There are also something like semi-persistent that get killed get deleted after a couple of weeks or a few weeks. And then there is the environment and scaling that we'll come to later. So this is how you control the number of nodes and tasks and the CPUs per task. So the first one controls the number of nodes that you ask for. Let's say you want 2 nodes. I said 1 here. You ask for some number of nodes. Then you ask them n tasks per node you can set up. Or you can also control how many threads per task/rank. This one is interesting because if you specify, let's say, 4 MPI ranks per node, and then specify by tasks per node 4 of those, and then you specify that you will have 8 CPUs on these nodes. 4 times 8, 32. So you will have 8 threads allocated per rank. So this is typically for hybrid jobs where you have a combination of a threaded model. Normally it's OpenMP and MPI at the same time. People do this in different ways, so it's hard to give more specific answer, but this is how you control it in Slurm. So this is a slide you could print out to have for reference. So we say 2 nodes, n tasks per node sets equal 2, and we have 2 CPUs per task. Then Slurm will set variables for us. The whole MPI environment is governed by variables. So if you print out the environment, you will see a lot of interesting things regarding MPI. Well, first of all, you see that it's allocated 2 nodes for us. There are 4 tasks, and there are 2 tasks per node, and there are 2 CPUs per task. So the Slurm variable n node set to 2, nproc set to 4, Slurm CPUs on the node is set to 4, and number of threads per rank is set to 2, which correspond quite nicely to what we asked for above. So this gives you a lot of room to play to find an optimum of how many MPI ranks you want to have and how many threads you want to run. There is no fixed answer to this question. And of course, with everything else in the world, when there are no good theory, you are set back to trial and error. And a lot of these things that I'm saying now or dealing with are actually found by trial and error. Some of the like scaling you can find, and that's an exercise later. But how many MPI ranks and how many threads per rank is not easy to know in beforehand. So trial and error. And most of people just accept something that they learned, but you should actually sit down and do some testing. What is the optimum mix between MPI ranks and threads? Yeah, Sturm also set MPI variables for MPI applications. As I said, this is if you don't have interaction or integration in the queuing system for MPI, MPI would set these for you. It's like PMI, MPI rank, local ranks, and rank IDs, and so on. The only thing that the MPI knows that when you start an MPI program is that MPI run will launch a number of executables on a number of CPUs on some nodes. Assume that you have 4 MPI ranks launched. They will be somewhere. They don't know anything, that they are not alone or whatever. They have no idea what's happening. They start executing the code. They encounter MPI in it. And after MPI in it, the MPI in it will read the variables in the environment. And then you get back 2 numbers. You get number what my rank is and how many ranks in total. That's about it. There are some other things hidden behind the scenes, but we don't really care. As a programmer, we don't have to care. But we do have to care about my rank, which is my rank number, and how many there are in total. And in this case, about 4. So we have 0, 1, 2, and 3. And I am, let's say, number 0. Then this is the only thing that we need to know as a program. And that is gotten from the environment. And most MPI programs are launched as single executable, just launched multiple times on different nodes, or the different CPUs. We don't know where they are launched unless you really do some specification on the Slurm. For most of the times, you can just launch them with m tasks equal something, and it will be okay. So pure MPI jobs are fairly easy to run. You just say that I want to run, and this is for Betsy. I say 8 nodes. I said n tasks per node is 128, and that will give me 1,024 ranks in total. So best practice is to use n tasks per node equal to the amount of cores in each node, if you want to do as many as possible. But you can start anything lower than that. But on Betsy, it's a bit problematic because you are only allowed to use scheduled whole nodes. But on Fram and Saga, you can schedule less. So especially on Saga, you can have you can launch an MPI job with 4 ranks, and it will be okay. So yeah, any kind of these. But you have to, if you go and run on Betsy, you'll probably have a good knowledge of how to behave, because you started off with the smaller systems. So running OpenMP jobs, threaded jobs. The difference between OpenMPI or MPI, or which I always say OpenMPI because it's the MPI we use, and threaded jobs are that threaded jobs are shared memory jobs. And shared memory is only possible within a single node, because there is no way we can address the memory in normal way, at least on other nodes from the address space that we have available. So shared memory is generally, in most cases, well, generally, there are exceptions, but who cares? I mean, generally confined to a single node. So there is only one node. Then you can say CPUs per task. That will control the number of threads. And you can check the scaling. You can see that you will get this open, the system will set for you the Slurm variables, CPUs per task, CPUs per node, CPUs on one node, and OpenMP, number of threads. OMP is a short for OpenMP. OpenMP is a very, very old standard for the threaded model. Because if you ever come across the book called POSIX threads, I'm tempted to say avoid at all costs, because no sane person will sit down and write the threads yourself with POSIX threads. That's why OpenMP and well, MP and later OpenMP came into existence to do all the bad work, all the bad stuff for us, so we don't have to deal with it. We can just set some directives in the compiler, and the loops and so on will get parallelized for us. So OpenMP is a very nice thing to have. It makes it, I can start parallelizing in 15 minutes. It's about playing chess. It takes 10 minutes to learn the rules, but it may take a lifetime to master it. So OpenMP and other programming in general is the same. It's very easy to start, but it's not so easy to master. So launching a hybrid executable is as simple as a normal MPI job, because you have already set the CPUs per task. That sets the OpenMP number of threads, and your program will pick that up, and it will launch the amount of threads that is set. And nothing else is needed for a simple run. No minus NP or minus PPN is needed. That's taken care of by Slurm. So don't do that. It could easily get into conflicts. Assume you have some stupid values set there, and you do something else in the setup with Slurm, and you assume that you get what you asked for, and you don't. So do not specify NP or PPN or something in the MPI run. Like a hybrid job, 2 nodes, 2 tasks per node, and 2 CPUs per task. That will give us 4 MPI ranks, 2 per node, and then 2 threads per rank. And we'll see here that you have hello world from the first rank, and then from each of the threads 4 times, since we have 4 MPI ranks. So this is a trivial example on how things are set up and how it's running. And be careful now, because is this the right number of ranks versus threads? Threads doesn't scale as well as MPI ranks, but in many cases, the limitation is not really in the threads or in the MPI. So where is the limitation of scaling? It's not trivial. So trial and error. Hybrid jobs are complicated. There are only one way of figuring it out. It's running a test example. Well, with the memory footprint of the real stuff, but very, very short runtime. So let's say if you're running a climate model, you could just do 1 iteration and then test with the different settings and see what's optimum. Because normally when you start running millions of core hours, I use core hours because Sigma 2 refer to CPU hours as core hours. Then maybe you are running in a suboptimal way and wasting millions of core hours, which is very bad. So I think most of the users should, every time they change models and so on, sit down and do a review of the best possible partition between ranks and threads. Which brings us to the next about resources, requesting memory. How much memory do I need? No, that's not easy to know. How you can do some guesswork and multiply by 2 and hope for the best. If you're lucky, your job goes through. And if it goes through without being killed by the out-of-memory troll, then you can actually review the Slurm file. I cannot state this too many times, and the importance cannot be underestimated of the real value of the Slurm log file. The Slurm log file contains a lot of clues to what's going on. So do read the Slurm file. Read it 5 times, 1 for each finger before you submit a ticket. And because you might already know before you submit the ticket after reading this file 5 times, what's the problem is, because there is a lot of, Slurm has gone out of the way to present you with good messages. So please do read the messages. In this case, we have some job statistics. This is called maximum RSS. RSS, you will also find it when you run the Pro in a little utility called top, that the maximum resident memory is the peak memory resident in the RAM, or the local memory, or the main memory of the computer. If you use more memory than the computer has installed, your job should actually be aborted immediately. Well, in most cases it is, because you cannot run with more memory than installed. For in most computers, it will write out the pages or the chunks of memory that you haven't been used for some time into the disk and reclaim it back if you need it. And if you do that over and over, your job will just grind to a halt. So it will not run at all. I mean, it takes 1,000 times longer time than it should. So I generally think that you should turn virtual memory off and then put a limit, and then so the auto memory troll will come out and kill your job. If you are using more memory than installed, then you should go to a bigger computer with more memory. Anyway, you can see here that you requested, or you have the maximum amount of memory used over the job, 248 megabyte. And then you could just ask Slurm to provide you with 300 maybe, 400, not twice the amount, but slightly more to be on the safe side. There are, probing for memory is not going on all the time, so it might be peaks. If you try to allocate, if you allocate 300 and you have 350 limit, and then for 1 second you try to allocate a bit more, you might be able to cheat on Slurm, so it won't be reported. But this is corner cases. But then the troll, auto memory troll, will come out and kill you anyway. So yeah, but you might get problem. But so put it a bit more than the averages, but not much more. Maybe less than the dump, not twice as much, but a bit more. If you get killed by auto memory, you know that you can request a bit more. Another thing is also fairly important. It's that storage during execution. In many cases, you have data that you read and write during a run. If you read in something at start and don't do anything more, input output until the job has finished and write it out again, this doesn't really apply to you. But if you in any circumstances do input output, read and write to the disk during a run, this is very, very important. But you can read those lines each time you are running something or change anything. You can read those lines and figuring out, what do I do? How does my job address the questions asked here? Especially the sequential or random access. At what size? If the size is small, your file might be cached within the memory of the compute node, and random access and sequential access will be identical. But if not, imagine that a file is a piece of, like a spool of tape. A hard drive is just some platters on disks where somebody have glued on pieces of magnetic tape. And then it's just a non-linear version of a very, very long tape, but the concept is the same. So think of a file as a long tape, and imagine that if you have to spool the tape back and forth all the time to get to read some sectors or some bytes that you want to read, it's very, very time consuming. Or if you, on the other hand, can put that file into some kind of memory, you can just ask for, I want to see address 5. And immediately, or almost immediately, that address 5, the bytes there will show up for you by magic. So like the memory. So be careful where you put the files during a run. If they are not much used, it doesn't matter. If they are a lot of use, it matters tremendously. Then at the beginning of the run, are all your files available? If you ask for 1,000 nodes, no, 1,000 nodes could be okay. Betsy has 1,300. Imagine that you ask for 2/3 of Betsy, and you are at the first time of your run of your script, you are copying a file, big file, really big one, because you're running on 1,000 nodes, so you could be a few terabytes of data. That takes quite some time. Even if you, let's say you copy it from NIRD, which is loosely attached, it might take 10, 20 minutes or even more. If you copy from one place to another, then normally we talk about 1 terabyte per hour. So assume that you are unlucky and you spend half an hour at 1,000 nodes. That means 128,000 cores. So just copying the file will cost you 128,000 core hours. So make sure all your data is available. Where do you store the output data? And error messages, logs, etc., that are not needed, they don't really need to be put on a file that you have to delete afterwards. So if everything is a normal run and you don't care about messages and so on, it's a very good idea to put those to dev0 or dev null. So just throw them away. So they are not copied to places, because most of the IO you do are done on a shared file system. And not only run it faster for you, but it will also lessen the load on a parallel file system, which is shared by everybody. So it's going to be better for anyone or everyone when you are using it less, which also come to local storage, scratch storage during a run. On Saga, it's limited to 800 gigs, so it's not that big. It should be bigger and it should be faster. We are working with this in the local system in Oslo, so those of you who run locally here could have more experimenting with this. But the thing is that metadata, which it touched upon, which is metadata, is every time you open a file, close a file, stat a file, or do some operations on the metadata on the file. If you do that on a parallel file system, it all centralized in one single metadata server. And if everybody does that all the time, that metadata server will become very loaded. And you can, in some cases, have situation where just doing an ls will take more than 1 minute or 5 minutes in extreme cases. It will bog down the whole system just because the metadata server is too busy. If you, on the other hand, run on a local file system like the Scratch file system, not only is it made by memory chips, so it's very, very fast, but you are essentially your own disk. So metadata operations are almost free of charge. They are not actually free, but compared to a parallel file system, you can think of them as zero cost. So if you can confine metadata operation to a local disk, it doesn't really matter. And if it does matter, it only affects you. Well, on Saga, it might all be sharing the node with other jobs, but generally metadata operations on local file systems are essentially free. So if you can use the Scratch files on during a run, you are in a good situation. But of course, it's limited to 800 gig. That's shared. If you are alone, you have the whole thing. If not, you have less, but you can request the size of the local scratch. So you can set it quite high. And in unlucky cases, you will have to wait until some node with that amount is available. Yeah, everything is easy with sequential access. Yeah, even a tape can handle that. That's actually quite true. A former colleague of me, he got more performance out of a tape drive than I could on a disk sequentially. So you can get, if you have very, very big files and read, you can actually read faster from a tape. But if small chunks, blocks or records, less than 0.5 MB, it's really bad. If you do sequential access and you are big files, it's so slow that you won't really believe it. I have some figures later on. If you are sharing data on several nodes, then you cannot use a local file system, because if the local file system is confined on each node. So there is nothing you can do with that. Storage for jobs. This is documented easily, so you can find all the things you need there. Here is the performance. You can see for random read, it's really, really bad. And you can see all the sequential read and random read and sequential write and so on. But I must say here that I have a very, very big file here. But if you have a big file, I took the times I run this IO zone job on Scratch, which is parallel file system. It took 20 hours. If I'm using local Scratch, it took 47 minutes. So you can think of how much you save it more than 20 times for just these simple IO zone jobs. So local Scratch is very, very, very good. But I must say, if I have a small file, like 4 GB, the random read is not so bad, because the file system can cache it for you either locally on the or on the IO servers. So it will be less bad. Yep. And binding, running threaded programs, OpenMP, that I think we already covered. You can review the slides if you like. There are some environment variables that you can set for OpenMP. This is for the NPB BT, which has some partial different equations. One of those was much better than the others. But on another benchmark, that might be different. It's also when you place them, you can place them by threads, by core, by socket. And for this for the BT NASA parallel benchmarks, for the BT benchmark in the OpenMP version, using cores is the better one. But that's not always the case. It varies from executable to executable. Running MPI programs, same thing. There are some options you can set, but this is advanced stuff. So if you want to really know about this, you have to consult the documentation. But I have some example here that you can see on the plot here, that you can set different algorithms for doing things. Integer sort, it's a well-known example where the application is sensitive to the algorithm for doing so. If you run Intel MPI, you have some lightweight statistics that you can play with. This is also a bit advanced. You have to read the manual. You can count up how many of the MPI functions that are called during the set. And you can see here is all-to-all vector, all-to-all V, that it's called a lot of times. Maybe the algorithms for that one, collective algorithms for that one, is not optimal. Trial and error again. Scaling. I try to look on my job, which is for the exercise also. The CPU efficiency was 82%. Is this good or bad? You can think of this until after the break when we have the exercise. Memory efficiency, that's not what you think it is. It's how much of the memory you allocated it used. So it's not how efficient you use the memory. So it's not that. If you want to learn more, we have the ARM performance reporter, which is a very, very nice utility that will give you a lot of interesting statistics, a bit advanced, so that you have to sit down and watch carefully what's going on, play with it and learn it. But I'm not showing you to tell you that this one is a very, very good tool for any performance. Before you start working on performance, run this and spend some time reading manuals and read what's going on here. If you want it even more advanced, you can have a roof line chart. And what you see is that most of the dots in your application will be below the line, which means it's memory bound. There are some dots above the line, which should be impossible, but the cache has more bandwidth than the main memory. So some of the dots are above, but the weight of these here will be sometimes most applications below the line. So most scientific applications are memory bound. It's also a bit advanced. So scaling. This is one of the things that you actually have to learn about. Perfect linear roll-off and negative. If you are on the blue one, you're absolutely well equipped. But in general, you are not. Very often you have the green one. That it rolls off and it goes slower the more cores you use. So the exercise is about scaling. I got this for the BT. You see, it goes slower with more 32 goes slower than 16. So why? And then the scale logarithmic here. So you could actually run, if you launched 2 jobs at 16 nodes each, you would get the performance of almost 13. But now you get only 4 if you are running with 32 cores. So then be very, very careful so you don't use more cores than you should. Check scaling. This is the exercise. Now we are approaching the end. So I used a little bit more than I went slightly over the time, but I hope that's okay.
That's fine, completely fine, Ole. Thank you so much. I was wondering, is there any question we want to take to discuss here? Sabri, Radovan, is there anything?
So, as always, Ole try to make it a little more entertaining and get these very extreme cases to explain things. So thank you, Ole. So when we look at our process, for example, if I take Saga, we have compute nodes with 2 sockets on each compute node with 20 cores each. And if we use a normal, like the way to find out threads, if you ask how many CPUs are there, it will tell us there are 80 because there's threads. So how do you interpret these numbers, and is it important to consider like which socket that we're using?
Yes, absolutely. And because I even have I could dig up a figure and showing you, because I actually run that exercise. If you run the memory bandwidth of what you could be referred to as remote memory, there are 2 sockets. If I'm a local socket, I have 1 memory bandwidth. If I run the memory bandwidth test with addressing and using the memory on the other socket, the memory bandwidth is 1/2. And not only that, but most applications are also not only sensitive to memory bandwidth, they're also sensitive to latency. A normal memory latency is about 100 nanoseconds if you access a random word somewhere. But if you do that on the remote node, going over the interconnect between the sockets and then using the memory controller on the other CPU, it's 300 nanoseconds. So it's a big, 3 times longer access time. So this is very, very important. I try to illustrate this with some of the OpenMP flags that you can set, but it's very, very important that you try to allocate local memory. So most of the times the operating system does it quite well for you, because this is a known fact for a couple of decades now. So the Linux kernel, the libraries and so on, try to allocate locally. But it's an interesting time if you run an application with NUMA control minus I, little I, and all. It will allocate memory around robin on all the memory banks around the system, and you will see how slow it goes. So yes, it's very, very important, but it helps that the operating system try to do as best as it can for us.
Another short question, Ole. So you made this point about not to waste resources while copying data. On an MPI job, if you think a job that run on Betsy or from something highly parallel, and if you have a lot of data, we can't use the scratch, if I'm correct, because multiple nodes need to access this data. In that situation where multiple shared memory threads need to access data, where do you stage the data and how to do it?
On Betsy, there is no local scratch. So the scratch is on the parallel file system. So that's okay. So in all of the systems have locals, have scratch that are shared. So the thing is to use cluster work users, your username, because that's a shared space with no limitations. You can put really big files in there and use that. Copy the files there, either manually on a login node or in on a serial script, or on Betsy. You can use the preproc node. Put the files there before you launch the big parallel job, because you cluster work users are available to anyone, and it's shared. But of course, if you start running a lot of things during a run there and put millions upon millions of files with, and then address them, like I saw a machine learning job that closed and opened and closed the files many times per second. Each thread did this, so the disk would grind to a halt. The process wasn't running, it was just hanging in disk wait. So then if that one had run on the local scratch, it would be good. But in the times where you actually need to share files between nodes, you have no choice. You have to use the parallel file system. That's what the parallel file system is there for, is sharing. So sharing is the keyword. If you need to share, sorry, I put in asterisk instead of swearing. So yeah.
Okay, thank you, Ole. Can I ask you a question regarding this climate model? You were saying that you may test with one iteration or something like that before we run the climate for the thousands of iterations. So do you have something to say about the system bias, which can be introduced with this parallelization, especially for the climate models?
Hard to tell. Hard to tell, because I don't really know the system bias and so on. Yeah. Climate models generally run the same. Each time step are fairly similar to each other, but not always. Yeah.
Not always.
But not always.
Yeah, it can create some kind of a small error, but it will accumulate with each iteration. Then it can be error. It can be a big error.
That's an inherited problem of all partial differential equations, because you each step introduce a small error. Yeah, but this is the programmer's problem, not my problem. Stepping a differential equation is notoriously difficult. So yeah, I know each of the errors accumulate, and this is very, very important for for everybody who are doing scientific work, that errors doesn't cancel, they add up. Even if you have errors that people think, oh, they will cancel because some are negative and some are positive, no, they do add up. But not all time steps are the same, because I remember in the job I had before, we were running the MM5 model, which is now called WRF, with the Met Office, and we were sitting looking on the Greater Oslo and following the execution, because it took half an hour or so to run through, or 20 minutes. So we were sitting and watching each iteration as it come. And then now we said, now the runtime will increase. How come? You know, at that point in time, it started to rain over Bærum. So it had a lot more work to do than when it's not raining, because there is a rain cloud model in there. So yes, all time steps are not the same.
I did run a MM5 model when after my master, so I knew that this issue.
Yeah.
Yeah. Okay, thank you. And we can take a break, but before that, Ole, we are going to have the exercise after the break. But
yes,
I thought we can stay on main room, and you can give a summary of how to do that. And you mentioned in the README file that plot the results. So do you have some plotting script or something else?
I don't have a way of plotting. I'm using a spreadsheet. I mean, people use a Jupyter notebook or whatever, but I start using a spreadsheet before many of you were born, because they came in the 80s. So I just use a spreadsheet and put in 2 columns of numbers. That it's very easy to do. But the exercise is about scaling. So
yeah. Could you give a demo on going through
I'll
the
give a
exercise?
demo on how to run
but
it.
After the break. Yeah.
After the break.
Yep. Yeah. We'll be back at 12. Take a little bit more long break. Thank you so much.
Yeah. Okay. Before I saw that the question number 14 about hyperthreads, I will deal with hyperthreads tomorrow. And I'll also show a drawing what's actually going on in there. So for those who are interested in the mystery and magic of the hyperthreads or virtual cores or whatever we would like to call it, seen from the operating system, it looks like they are twice as many cores as they are, but they are actually threads. But a modern CPU is a very complex piece of machinery with many executional units inside, so the picture is a bit complicated. So I have a drawing tomorrow that will try to explain, but
thank you. And you can copy this exercise files from the directory inside the project directory. So cluster projects and 984K, best practices, day 1, and scaling. I have copied your directory here, Uday. So there is an README file, and you can use the training project NN9984K, and there is a reservation for this course, so that you don't need to wait in the queue. So you can use the reservation and best practices. Can you take over from me, Ole, and show one of the demo?
I have already put that into the script. You see if I can share the screen.
Yes.
Share screen.
So we plan to do this on main rooms, and you can ask question on the collaborative document as well as raise the question here.
You see my screen?
Yeah. I could see your desktop.
Yeah, with this window that I'm typing in now. Yeah, very good.
In the terminal and also the part of your desktop, if you want to hide it.
Both desktop, no, the one with the Emacs and so on. I think it's only one, because I have 2 screens. So no, the desktop is nothing secret.
Okay,
so that's fine. Otherwise, I could just fill the whole thing with the terminal, but yeah, doesn't matter. I can move this away. Right. So the thing with this one is to actually check scaling of an MPI program. Their MPI program is actually put under bin. There is a this is the NASA parallel benchmark. They are very, very old, but they are copied out of real applications and just put into some miniature mini apps, or what you like to call them. And some of the benchmarks address different things, but it's my favorite because they've been used for so long time and everybody knows these ones. This is SP is part of the partial differential equations. And I deliberately chose a small scale one that has a small memory footprint. That's why it fit into 500 gigs of memory. So it's easy to run. I mean, I've already prepared a run file. I generally call my scripts run script.run. It's best practice, or no, well, if you call them SH, it's not so easy to know if they are just a script to be run or it's as a bash script. Some people call them bash or slurm or whatever, but sp.run is my way of doing it, which is what you'll see. I have here put in, this is my one, I put in some other stuff here, but you use the account 9948. This is my test account that you will not be allowed to use, and we have a reservation which is set aside that we have a reservation called NRIS best practice, with some nodes are reserved for us, so it will probably start immediately. Then I could put in 4 and up to 81 and so on, but I'm not sure how well 81 will go with only 2 nodes. I thought we had more. Memory per CPU, 500. In this case, is 500 megabyte per rank. And how many ranks are given with the number here. Then I load the module for OpenMPI. Then I run. I use MPI run. I could have used SRun. So in order to run, capital letters, SBatch and sp.run, that will submit the job. While we wait for that, we can say SQ and my username. It's scheduled on C320. What we can do is to log into that one. This is an interesting thing. Most of you can only log into 2 nodes that you have a job running on. I can log into anyone because it's heavily loaded. As I talked about earlier, if the node has a lot of load on the IO system, or in this case, a lot of people are running the benchmark, which is a good thing. See, a lot of people are running SP. And you can see how many they are running. Yeah, there's a lot of SP benchmarks running, which is a good thing. Top is your friend. Top will give you virtual memory, which is a theoretical number, but the resident is the important. This is the RSS resident memory. It's another, the other one you see in Slurm is RSS, but here it says res. Resident memory is the actual amount of memory being used on the physical memory being allocated. Shared is some buffer set up for sharing. CPU is percent CPU. So if you use 100% of one CPU, it's 100. That number, if you're running multi-threaded jobs, it could be a very high number. And it could be 4,000 if all the 40 cores are used. And the percentage of memory that you also use can also be interesting numbers to have. Of course, you can press uniform and give your user, you will see only yourself. You see Slurm script is running here, MPI run is running, top is running, and sp.b.x is running. And there are a lot of other things. If you press 1, you can see all the CPUs, but there is no room for all of it here. So top is absolutely your friend, Q. And I'm not sure if HTOP is not installed. There is another top that can give you some bars and so on. So is the job done? No, not yet. You see, you got number of processes 1. This is not very good. I mean, there's only 1 here. No wonder it took some time. It's done. We should run it with more. We should run it with a lot of more processes. Anyway, what you get out here is millions of operations per second in total. Then it's also millions of operations per second per process. Since we are running 1 rank, we are getting the same 2 numbers. And if we are lucky, if the program scales perfectly, we will have the number of millions of operations per second per process should stay constant if we have perfect scaling. So what we can do now is to say, we open up Emacs and we change this to 4. It will not run on, I don't think it runs on 2 because it runs on squares. Now we change this one to 4. There are different ways of doing this, but the end tasks equal 4. And we run SPatch again.
So you have aliases for these commands, right, Ole?
Well, I have.
And for SBatch and all?
No, I run, sorry. If you do exclamation mark, I can just say SPatch, and it will try to search backwards and repeat command that maps the last command done that maps to SPA. So if I type L, it should probably, no, it won't. But if I say SQ, it will map SQ. If I say SPatch, it will just map like grep up from your history file and like history. And if I say SQ, it will see that this is the first one in the history, the latest one in the history that maps to SQ. If I say S, it will complain because it doesn't match, because there are several matches. Probably if I just said S, it will take SQ. Yeah, it maps the first one in the list. Now it's already done. So yeah, it's not an alias, but uses of exclamation mark. So that's a little neat. It's a little neat trick in Bash. But of course, there's a lot of things in Bash. Yeah, it's a lot of things in Bash, because if I say I can run the keyboard, and this is the beauty of running Emacs over any of the other editors. It's a reason that Emacs is called the king of editors. If I now want to search backwards in the history, I can use Emacs character mapping. I can say Control R, which is reverse I search on Emacs, and I can say SQ, and it will come up with this one. So the character mapping on the command line in the Bash script and on the Bash command line and the Emacs are the same. So if I say ls minus L, and then I go back here and do a Control K for kill, I can yank it back with Control Y. So, but the point is that we now have a Slurm file called 764, and I press tab, which is the expanding. So I'm not sure how much we talked about tab expansion in the first session. I don't think we did spend too much time on it. Anyway, try always to run tab, and it will try to expand if it can. Total number of processes, 4, which is good. Verification successful, that's almost always the case. But now we have more million operations in total. We have 2013. I recall it was slightly less last time we ran, but it's about the same. So now we're lucky because this one is about the same as the other one. So now it scaled very, very well from 1 to 4 MPI ranks, which is good. We can now, if I does this, it will open up Emacs. Now we can try with 9. Now I'm not sure if I managed to log into C310 before it stops. I don't think I'm alone in here because it's very slow. So yeah, if I now take my username, you'll see that I have a lot of these running. It should be 9 of them if you count them. So when you're running MPI, see here that process ID, which is the number of the process. Each process is an individual program. It's done. So each process ID is an individual program. There is nothing shared between the MPI executables. They are all the same. They are totally independent of each other. The only way you can interact from one MPI rank to another MPI rank is through the MPI interface. MPI stands for Message Passing Interface. So the only thing I could do is to send messages from one rank to another. On a high level scale, you can also do collective operation that operates on more than one rank, like all-to-all or broadcast or gather or whatever, or scatter gather. A lot of or barrier is the simplest of them all. Barrier holds until everybody is on the barrier. Like when you're starting horses on a horse race, you have a barrier that the horses approach, and then when everybody and all the horses are there, you release. Same is barrier, which is the simplest collective operation. But generally, all the MPI ranks are totally independent of all other MPI ranks. So log out. We'll see now. Slurm. S doesn't help us. There's a lot of things. When I press tab, you see there's a lot of things. I press Control L, which is an old character from the teletype units, which mean form feed, that is scroll out the paper 1 page. So that still works today. It clears the screen, but it actually scrolls screen 1 page. So I have to say slurm. Okay, this peeps, and then I can take 72 is the last one. So now we arrive at an interesting point here, because now we saw we had 1900, we had 2000, we had only 1700 this time, but the number of million operations per second in total went up to 15,000. So almost a doubling, but not quite, since the operation per process is less. And of course, we could dig out something here. You see the maximum memory, 281 megabyte. I asked for 500, so that's slightly less than double, which is okay. I mean, this is so small. Emacs, we can now go to, we can say 16th. We have time to run more. We can run something more in parallel. We can say 25. I have 2 of them running. You can see one of them is actually spanning 2 nodes. the other one is only on one node, but the last one I submitted at 25 ranks, it's spanning 2 nodes. You can always log into systems that are running. If you have something running there, you're allowed to log in. Here's a lot of them. You can also see the load average on top. There are 16, or 17 now. 16 is that there are 16 jobs in status running. But you see something here, it's something in disk weight. Disk weight is very, very bad. It's really bad. If it stays on for a long time, it's a sign of something very wrong going on. And this time, the disk weight is here because they are waiting for the disk to respond. Especially when you launch big jobs like this, it will take some time to read all these MPI executables from the disk. That can take some time. So, but you see now they are running. So a few seconds in disk wait is okay. But if disk wait is in or stays there for a long time or is constant, then it's a sign of something terribly wrong, because it's waiting for the disk to respond. It doesn't consume any CPU, but it comes up at load average because there is a job that could run if the resources were there. So it's not really sleeping or non-runnable. It is runnable when it gets the resources. So my job is finished. We can do aha. Now we are down to 987 when we are running 16. If we run the 25, I think it was because there were too many jobs running. Now we are down to 1200, but we are up to 31,000 or 32,000. What we can do now is to run at even higher. We can run at 25, no, at 36. Arrow up works nicely. Same character, same key mapping as Emacs. 3.6 at 49. Now it starts to get interesting. But now we are using quite a lot of resources. Now it's pending. So I cannot run more because there are too many jobs submitted in that queue. So it's status pending. It's waiting to be run. Pending. But I can show you another trick. If you want to follow the Slurm file, 89, I take tail minus F. F is follow. Small f is if the file exists. Capital F if the file is not existing. So we are waiting for it to be called into existence. It's done. And how much did we get here? 1100. But the total number increased. So we now have the efficiency or per rank is 1100. Remember that we were close to 2000 before. So now we are down to only 50% of the utilization that we got earlier on. This is a sign that we are probably using too many ranks. Even though the total number here increases, but we run with many more ranks and less efficiency per rank. So now we are approaching the limit of what we can. Look, C for scaling. Slurm 91. 49 processes. I got 1300, but this number increased to 67,000 or 68,000. Do one more before I dig up a plot I made earlier. I ran this yesterday also. It's faster to just use this one than to arrow up. This is a trade-off, how much arrow up you want to do or how much exclamation mark or Control R. This is something that you have to learn. Exclamation mark, Control R, and arrow up or down or whatever. You can also search forward, but Control S if you are done, but the Control R is the most common. Pending on priority. Yeah, 81. As you probably figured out, this is a square number. Okay, it's not allowed. But see, look here already now, SPatch gave me an error. Batch job submission failed. Okay, I already noticed that. I understood. I got when I get error, something failed. But it requested node configuration is not available. That is because there are not enough nodes set aside to run this. I asked for 81. There are 40 cores per node, and I asked for 81, which is one more than there are reservation for. So I cannot run this one. But this is pending. So
yeah.
I think, yeah.
Ole,
Question,
we are reaching time in 5 minutes. I was wondering whether you can summarize with the plot and everyone can play around.
I already did so while I understood why you were cutting me off. So this is what I got yesterday. You see, this is really, you see, it grinds to a halt at 64 or 81. It did yesterday. But if you look on the numbers, they are terrible. I mean, I got numbers up to 52,000 at 49 maximum. And at 64, I got 1100. So it's something goes haywire at higher core count. But I've seen from over and over again that people run with too high core count and are wasting resources. And it's not always easy to spot. There is an example then when we had something called instructions per second, which is generally a good measure of how well the program ran. Then we saw that WASP was running very well because it had a very, very high instructions per cycle number. So it was running very, very efficient. But the program didn't scale. So when we looked further into it, we saw that it spent all its time in a function called MPI wait. But it did so very, very efficient. MPI function wait all was very efficient. So it was waiting very efficiently, which is very bad. So this is just to illustrate how hard it can be to figure out misbehavior, how things are actually working behind the scenes. It looked like it was running well, and it was, but it was running well in a wait function. So you're wasting resources in a very efficient way. So some kind of things are what's happened here at 64 and 81 cores. So I urge you, before you embark on something that uses 10 or more or 16 or more cores, look into scaling, because you might be running here at 64 cores at shitty performance when you should be up here, or maybe best at 25, because this is, you see the going from 25 to 49 is almost a doubling of the number of cores. Doesn't give you anything. So please do check the scaling. And I think we run out of time because we need some minutes for Danya to wrap it up. Thank you very much.
Thank you so much, Ole. It is very good that you did the demo, and it was very useful. So I was, the node reservation and this training project will be available rest of the day and the next 2 days. So you can play around a little bit more, provided that you have an account on our system. So that's there. And tomorrow, Ole will continue with more tricks to troubleshoot these issues on the clusters. And we will have sessions on how much memory to choose and how many cores you need to choose. So before I wind up, I would like to get your feedback on the collaborative document. End of the document, we have asked for feedback. So one thing you thought was nice, or one thing you thought that we should improve the next days or the coming event. So that's all from me today. And I would like to thank you all the instructors, Einar, Ole, and Björn Helge, for these wonderful sessions, and all of you to join us to learn more. And there are people behind scenes who is answering your questions on this collaborative documents. So thanks to all of them, and I hope to see you all tomorrow. So we are wrapping up here. Thank you.